Hey, we're going to talk about electric fields. Here is what the IB syllabus says you should know about electric fields. And electric fields, just before we begin, I want you to understand, are a very esoteric concept, very abstract. This is kind of weird stuff, all right? But you should be able to define what electric field strength is. You should be able to determine the electric field strength due to one or more point charges. We'll talk about how to do that today. You should be able to draw the electric field patterns for different charge configurations. We will also talk about how to do that today. And you should be able to solve problems involving electric charges, electric forces, and electric fields. Those are the things that I would like for us to cover today. In some ways, this will be a little bit easier because we've already talked about gravitational fields. And fields are fields are fields. Right? That's simple stuff. We've got electric fields, we've got gravitational fields, we've got magnetic fields. Today, we're going to focus on the electrical ones. And it all began with Sir Isaac Newton. Yeah, go Isaac. Isaac Newton was a brilliant man who gave us a lot of great stuff. And one of his amazing discoveries was to develop our understanding of gravity and come up with the law of universal gravitation. When he did this, when he recognized that the same force that caused an apple to fall to the earth was the same force that keeps the moon in orbit or keeps the earth in orbit around the sun, that was an incredible revolution. But there was one thing about it that he hated. And the thing that he disliked about it was the fact that this gravitational force could act over millions of miles without there being an actor, without there being a cable or something to exert that force. He disliked it immensely, and he was never able to really explain it. The reason he disliked it is because it felt a lot like magic. The sun's pulling on the Earth 93 million miles away and keeping us in orbit, and yet I can't see or feel or comprehend why it's doing that. He did not like that, and he never did come up with a really good solution. Field theory is a way of getting around that idea, and generally this is kind of what it's like. If this is the sun, and here's the Earth, there's 93 million miles there, and we know the sun's pulling on the Earth gravitationally. Newton didn't like that. What field theory says is, well, you know, really, and it's kind of semantics, but it's just a different way of imagining it. Rather than the sun mysteriously pulling on the Earth, actually what field theory says is, let's forget about the Earth for a second. The sun is actually doing something to the space around it, creating a field, a force field, okay, an energy field, creating an electrical or a gravitational field. Because there's this field in space, when I put the Earth in the field, it's the fact that the Earth is interacting with that field that the Earth feels a force. So it's just a slightly different way of perceiving what's going on. Rather than this mysterious thing pulling, instead, there's something happening to the space around the sun, and the Earth is interacting with that space. That's the general concept of a field, okay? What you need to understand is that space is not uniform. Space is not uniform everywhere, and it's not so hard to grasp that concept. If I had a super strong magnet, if I had a huge magnet right here, you would know that if I put paper clips near the magnet, they would act very differently than if I put them far from the magnet. The space around the magnet is different than space far away from a magnet. If I reached into my pocket and I pulled out a black hole, space around the black hole would be very different than space not near it. It's not uniform. Okay, so this idea that space is not uniform is fairly easy to grasp. The same is true for an electrically charged object. When something is charged electrically, when it carries a positive or negative charge, it affects the space around it, and we can actually demonstrate that with our Van de Graaff. You can think of this non-uniform space, you can think of them as being force fields, okay? Just like in Star Trek and Star Wars, we have force fields. They do exist. This idea of a field does exist. But a better name for them, rather than force fields, might be energy fields, because the idea behind these fields is that energy is stored in them, either gravitational energy, electrical energy. Those things can be stored in these fields around objects. So the concept of the electric field was really developed and refined by a physicist whose name was Michael Faraday. And Michael Faraday is a really interesting historical character in the world of physics. Absolutely brilliant. He was one of the prime scientists of his age, and he became the head of the Royal Institute, which is huge in England. but he could not do math. He couldn't do math, right? He could not read the mathematical papers of his contemporaries. But he was brilliant in being able to conceptualize what was going on. And some people credit his inability to do math with the reason that he came up with field theory, because he was actually, since he couldn't calculate what was going on electrically, he was able to visualize these electric fields better than other people could. So he came up with the idea of electric field theory, and here was basically his definition. Here was how he was going to map out what an electric field might look like. He said, hey, let's take a small test charge, a small positively charged object. The smallest we can get, reasonably speaking, would be like a proton. And if you take a proton and you measure the force acting on it, it tells you something about that field. And as you move it around and look at the forces that are acting on that positive test charge, it can tell you how strong the field is and what direction the field is acting. It's very, very important that when you do this, that your test charge be very small. The reason for that is you don't want your test charge, the thing that you're using to map the field, to be creating its own electric field and disrupting what you're trying to observe. So ideally, it would be infinitely small so that it doesn't disrupt what you're mapping out. But you take the small positively charged object and you move it around, you look at the forces acting on it, and that can give you a map of the electric field. So for example, if I have a positively charged object here, and I bring my little positive test charge and I place it right there, what direction does it feel a force? Away, towards me. So it's going to be like that. Awesome. So I know at that point, that's not drawn quite the right direction, but the electric field is in that direction right there. How about if I placed it right here? It would be down. How about if I placed it right here? It would go down and be stronger, correct? Okay? So by doing this all over the place, I can start to get a map of what the electric field looks like. Out here, it'll be a little bit weaker. Over here, it would be much stronger. I get an idea of the direction and the strength of the field by taking a small positively charged object and seeing what forces are acting on. Okay? Let's look at electric fields now a little bit more mathematically. Our definition of what an electric field is the force that a charge feels divided by the charge on that object. That's our definition of electric field strength. Electric field strength is represented by capital letter E, and you can calculate it by how many newtons of force an object feels divided by how charged that object is. That will give you the strength of the electric field at that location. Okay? There's a second equation, which is not in your data booklet, but which will come in really handy, and it's very easy to figure out. And I'll show you how you do it. Notice that we have force. We have an equation for electric force. We've been using it. What is it? Coulomb's law. KQ1, Q2 over R squared, or D squared. R and D can kind of be interchangeable. Notice that electric field strength is defined as the force divided by the charge that's feeling that force. And in this case, one of the Q's cancels out, and I get left with this equation right there. Okay, good question. That's a great question. Take a look at different Q's in both of these two equations. In this equation, in the first one, which is really what, this is in your data booklet, this is our definition. This Q is the charge that's feeling the force or feeling the effect of the field. Whatever's in the field, that's it. This equation allows me now to calculate the strength of the electric field a certain distance away from a charged object. So this is the Q that's creating the electric field. Does that make sense? Okay. So for example, I have a charged object here, and I want to know, hey, how strong is the electric field over here that's created by this charged object? I would use this equation. On the other hand, if I place a charged object in space and it feels a force, and I want to know the strength of the electric field at that location that was created by some other object, I would, bless you, I would use the charge of this object to figure out the strength of the electric field at that location. Does that make sense? Recognize a couple of things about this, you guys. Two things that I want you to think about. First of all, the units for field strength are newtons per coulomb. In some ways, I think that helps. If you think about the units, I think it helps give you a concept of what fields are. So if I have an electric field right here that has a strength of 10 newtons per coulomb, and I take an object now that has 1 coulomb of charge on it, and I place it right there, how many newtons of force will it feel? 10 newtons. What about if I take an object that has 3 coulombs of charge, and I place it right there? 30 newtons of force. So field theory tells me something about the location. When I put an object in that location, I can then figure out how much force it will feel. Does that make sense? Okay. What if I put a neutral object in that location? How much force will it feel? 0, because it doesn't have any electric charge. Excellent. Okay. The other thing is to look at this equation for a second. This is how it is in your data booklet. It's very easy to rearrange this equation to say this. The force that an electrically charged object feels is equal to the strength of the electric field times the charge on that object. That comes up a lot. You will use that a lot. Okay? The force that an object feels is equal to the electric field strength times the charge. This is electrical force. Notice this is very similar to the gravitational force that an object feels is equal to the mass of an object times the gravitational field strength. Ooh, we've always said F equals mg, right? Or weight equals mg. Same idea, except for now instead of a gravitational field, we're talking about an electrical field. Instead of mass, we're talking about charge. Concept's the same though. Okay, Isabel. Let's compare it to gravity, but I just kind of did. Anybody need any more comparisons with gravity? Kind of how similarities there? Okay. So now, the final thing, that was kind of the mathematical way of dealing with electrical fields. There's a visual way of drawing electrical fields, of mapping them. And in some ways, this is similar to like a topographic map. How a topographic map can show you elevations, well, an electric field map can show you force fields and how those work. Oh, no. Okay. There are some rules. We draw electric fields by using what we call field lines, drawing lines. And this was something that Faraday visualized for us. And there are some rules when you're drawing electric field lines. The first rule is that all field lines will go from positive to negative in an electric field, okay? And that makes sense because remember, we're defining them with a positive test charge, so they will be repelled by positive objects and attracted to negative objects. So when drawing the field lines, they must start on a positive and end on a negative. Whenever a field line meets a charged object, it will meet it perpendicular to the surface. It'll meet it at right angles. I'll show you some examples of this in just a second. Field lines never cross. They never cross one another. The density of the field lines indicates the strength of the field. Please remember that fact. It will help you. The density of field lines indicates their strength. On a topographic map, what do the lines on a topographic map tell you? Elevation. And if they are very dense, if they're very close together, what does that tell you? Very steep hillside. Excellent. In a field strength, the density of, or in a field map, the density of the lines tells you the strength of the field, okay? Exactly. And inside of a hollow conductor, there is no electric field. Remember we were talking about that the other day with charge. Inside of a hollow conductor, the net charge is 0. Well, it turns out there's no electric field inside of a conductor, and that's why we get those cool Faraday cages, and we have, you know, you're safe when you're inside your car when lightning strikes and things like that. Okay. Yeah. Okay. And then I'm gonna show you some examples of electric field lines here in just a sec. Okay. I just placed a charged object on the screen. This cool little computer applet created the electric field, drew the electric field around it. Only one thing is missing. It's a positively charged object. It's a little red dot. You can barely see it. What's missing from these field lines? Arrows. Thank you very much. And what direction should they go? They should be If we were to draw arrows, they should be going away from this object, because remember that the field is defined as the force that a positive test charge will feel, and in this case it would be repelled. Notice that if I make my charge, has a charge of +1. What if I make it bigger? Let's go up to +8. Hey, look, more field lines. The field is stronger, right? There's a higher density of lines. And you can also tell that right here, the field is stronger than right here because the density of the lines is greater, okay? So you can assume from this that, hey, the closer I am to an object, the stronger the field. But you don't have to assume that, because you know this. Of course, the closer you get, the stronger it is, because they are inversely proportional to the square of the distance. Isabel had her hand up first. So check it out. So notice that here is a negatively charged object. Let's put a positively charged object in there and see how it affects the field. Oh, look at that. Now we have a new electric field created by two objects, okay? And again, the one thing missing is arrows, but you guys know that the arrows go away from the positive and towards the negative, right? And what this tells me now is if I place a charged object in that space, I can figure out the direction of the force. If I place a little proton right here, it's going to feel a force that way. If I place a little proton right here, it's going to feel a force that way. If I place an electron right here, it's going to feel a force that way. Okay? And I can also tell that it will feel a stronger force here than it will out here. That's what drawing the electric field does for us. Let's look at what happens if I put two positively charged objects in there. Okay? There's a positive. There's another positive. Okay? There's the field. Exactly, because if I place something right there, what force will it feel? Nothing. The net force will be 0. Okay? Because it'll be attracted to both or repelled from both. Or a proton. There's. Now, obviously, this can get a lot more complicated, right? We can do crazy things and do more crazy things, right? Okay. Look at that. Okay, there's our crazy electric field now. Hey, Skylar, we're missing you, man. What are you doing? Come join class. Hope you're all right. Okay, here's what I want you guys to do. On a piece of paper or on the back of your friend's shirt or whatever, draw these 4 situations, okay? Draw the electric fields for a single negative charge, a negative point charge, a positive and a negative charge that are near each other but not touching, okay? 2 positive charges that are near each other. We just did those on the board, so if you're paying attention, that should be facile, okay? And then 2 parallel plates that are oppositely charged. And what that means is, like, if I have a metal plate here and a metal plate here, and one's positive and one's negative, what would the electric field look like in between those plates? Please remember that field lines have directionality, so they need to have arrows. Don't just draw lines, but draw arrows, okay? Number 2 should look something like that. Yeah? Okay? From the positive to the negative. All right? I don't know that it has a name. It probably does, but I don't know what it is. Okay, 2 similarly charged objects. That's what they would look like. If the 2 charges were negative instead of positive, how would that differ? Just the direction. Okay, the pattern would be the same. The arrows would be the opposite direction. What if this charge was twice as large as the other one? What would happen? Okay. It would look very similar. The lines, there'd be more lines around the right one than the left one because it's stronger, and this null zone in the middle would shift over to the left a little bit. Does that make sense? Because you still have a region of 0 field strength, but it would be closer to the weaker object. Excellent. And the 2 charged plates, which we haven't really talked about at all, would look something like that. Okay? It turns out that between 2 parallel surfaces, remember the field lines leave and reach the surface parallel, okay, and they can't cross. So what you're going to get inside of the 2 plates is a very uniform field strength, very constant field strength. This is really useful. We use it in a variety of technologies. At the edges, Kyle, what you notice is that they do curve a little bit. That's just called the edge effect. And why does it do that? I don't know. And do you need to know it? Yes, you should know about it. But usually when there's a question about charged plates, what we're dealing with is this uniform field inside of the plates. Okay? So what's the point of all this? How is it useful? Well, one of the classic experiments in physics, one of the most important and just elegant experiments that ever happened, the oil drop experiment, uses this technology. And it was an experiment that was conducted in 1910 by Robert A. Millikan. He was a physicist here in the U.S., and what he was able to do, this is called the oil drop experiment, and he was able to measure the charge of the electron. Now think about that for a second. I tell you that an electron is charged 1.6 times 10 to the negative 19th coulombs, and you guys are such awesome students that you believe me, okay? Which is great. But what also might have crossed your mind, and hopefully did at some point, is how do they know that? How do they know? I mean, do you take an atom and you get a really tiny pair of tweezers, and you go up and you grab an electron, and it squeals, and you take it and you measure its charge, right? No. You can't do that, right? They're too small. You can't do it. So how do we know? This is how we first figured out the charge on an electron. And Robert A. Millikan, he did win a Nobel Prize. Very smart experimental physicist. Here's the experiment. You don't have to know this in great detail. I just would like you to be aware of it, because there are some classic experiments that have happened that are good to know about. He took this thing called an atomizer, okay? An atomizer is, you can think of it as being like a perfume little squirt bottles thing, right? You got some liquid in here, you squeeze the bulb, and stuff comes out, okay? You guys know what I'm talking about? Okay. He didn't use perfume in this case. He used oil. So he would shoot little drops of oil out, and they would come out and start falling down because of gravity. But he also had it set up so that they would become charged due to friction. Remember, we can charge things with friction. So as the oil drops came out, they were becoming negatively charged. He had a charged metal plate that was positive. He had another one that was negative. The upper plate had a hole in it. He could actually adjust the voltage to create an electric field, okay, in between these two plates that looks something like this. Now remember, these are negatively charged drops, so they're going to feel an electrical force opposite of the field. As they're falling, gravity's pulling them down. Some of them fall through the hole and continue to fall. They have a charge on them. He adjusts the voltage, looking through his viewing microscope, and he adjusts the voltage until he can just get one of the drops to hover. Okay? So he sees them falling, he turns up the voltage, they're slowing down, and as soon as he gets one to hover, he stops. And he measures the voltage. And at that point, what he's done is he's got an oil drop that has gravity pulling it down and exactly the same electrical force holding it up. Make sense so far? So you can say that the gravitational force is equal to the electrical force. He knows the strength of the electrical field because you can figure that out with distance and voltage and things like that. And so by taking this equation, he was able to calculate the charge on the oil drop. Now that was not the charge of the electron. That was just the first step. Think about this for a second. Because each oil drop didn't just gain one electron. Some of them gained 12. Some of them gained 4,000. Some of them gained 896, okay? So he did this over and over and over, and he measured the charge on each and every oil drop that he was able to capture. And what he noticed was there was a common factor of how charged each oil drop was. He noticed that each oil drop could be some multiple, some whole number multiple of the same factor, and that factor was 1.6 times 10 to the negative 19th coulombs. And that is how he discovered that the charge on an electron is 1.6 times 10 to the negative 19th. So that's Millikan's oil drop experiment. Pretty good one. Okay. Here are some practice problems that, because of the nature of the day, we're not going to have time to work on them. But Sky, you can do them. Do them, Sky. Do them. And you too can go home and try them, okay? Because the more you do, the better you get at this stuff.